Okay, so for coherent sheaves, I and J are both finite. So locally, M is finitely generated with finitely many relations. Okay, so now our X is an algebraic variety. And hence Noetherian. And hence any.
Извините, а почему не глобально определены конечными соотношениями и образующими? Почему это не видно из точной последовательности вот этой квазикогерентных очков?
It's only local. It only holds true locally. You see, it is not. It does not hold globally. It's only locally. Only over open subsets. Okay, maybe I should write U instead of X to stress this point. Okay, thank you. Welcome. And it means that any subsheaf, say N, of a coherent sheaf is coherent as well. And when I write a subsheaf, I presume that it's subsheaf of OX modules. Well, okay, any, maybe I should say any quasi-coherent subsheaf of a coherent one is coherent as well. Okay, now as you remember, the main result of the last time was an equivalence. So we had, in case X is affine, then we had quasi-coherent sheaves on X, and there was a function of global sections to A modules. And there was a function of localization back, and these were mutually inverse. Exact equivalences of abelian categories. Okay, and now inside quasi-coherent sheaves, we have a full subcategory of coherent sheaves, and on the other hand, inside of A modules, we have a full subcategory of finitely generated A modules. And again, by Noetherian property, they automatically have they are finitely present, have finite relation. So I claim that the above equivalences restrict to the same equivalences of those finitely generated modules with coherent sheaves. So this is gamma, and this is localization, and this is an equivalence. And this is the subject of the next proposition.
Oh, and by the
Yeah.
way, are these
Yeah.
are these functors of taking global sections and localizations exact if
Yes, yes, that's what I said.
x is not affine?
No, by no means. No, by no means. Already for projective line, for any, yeah, and you can construct a counterexample easily, and we will discuss it later on. And
Okay.
never, it's never more, only for affine. Okay, so the proposition claims just this, that say for M and A module, its localization M tilde is a coherent sheaf on X if and only if M is finally generated. Okay, and the proof is easy. So if M is finally generated, then its localization is coherent just immediately from construction. Yeah, you just tensor this finite presentation of M with OX, and there you are. Conversely, we have an open covering, but by the definition of coherent sheaf, and since X is quasi-compact, we may find a finite covering. X is the union of the basic open subsets, and if we restrict the we have some coherent sheaf, say M calligraphic. So if we restrict it to these open subsets, then we know that they are finitely presented. So in other words, they are localizations of certain modules of finitely generated models Mi over the localizations A Fi. Okay, and it means that we can find. So let's choose the generators of all these modules. Let's denote them, say, mu ij, and they are of the form certain mij over fi to some power dij. Okay, so the generators of mi, and there are finitely many. So j runs from 1 to something, say ki.
Это каллиграфическая, вот здесь вот.
Who is calligraphic once again? Say it again.
Генераторы μij являются генераторами какого модуля? Обычного или вот каллиграфического? Немножко.
So this our quasi
вот это mi, да? Вот это mi.
Is a localization of a certain finally generated module over localization of our ring A, yes, and on the other hand, we know from the quasi-coherent theory of the last time that those M sub i's are in turn localizations of our M itself. Okay, so Mi is M localized with respect to Fi, and M is just the global sections of our quasi-coherent sheet. Okay, so we already know the localization theory for modules. Only we want to keep track of finally generated property. Okay, otherwise everything's fine. So all those local generators, they come from global elements of M. Okay, so those Mij, they all lie in M itself, but then we just add some denominators. Okay, fine. So we know once again that all those localizations, capital M sub I, are finitely generated. Now we consider a submodule, say M prime inside, or maybe okay, a submodule M prime inside M generated by all those Mijs. Okay. Sorry. Then, if you consider the localization, we still have a subsheaf like this, but on each UI, this embedding is actually an isomorphism. Okay, and hence M tilde prime, actually this embedding is an isomorphism into the localization of M. Okay, but then from the quasi-coherent theory, we know that M prime embedded into M is actually the whole of M. Okay, so there we are. And now let's consider some examples of coherent sheaves. Well, we can start with the most trivial thing, just OX is coherent. And now suppose we have a closed embedding, say I from X into Y, a closed embedding. Of algebraic varieties. Now I claim that given a coherent sheaf on X, its direct image to y is a coherent sheaf on y. So first of all, you have a surjection from OY onto OX, right? Locally, it's a closed embedding, so locally X is given by some equations, and there is a projection from functions on Y to functions on X. It's a surjection, and so for any sheaf, say M of OX modules, it's push forward to Y is an OY module, but it's supported on X. And now if M is coherent, then its push forward is a coherent sheaf on Y. Okay, again, this is just a local question. You have a finally generated OX module, then it's a fortiori finally generated OY module. Okay, and somehow maybe how to say it, conversely, there is a way to construct coherent OX modules from OY modules, from coherent OY modules. And this is the so-called restriction to X. So how does it work? Well, you see that there is an exact sequence, 0 to the ideal sheaf of, well, maybe it's a sheaf of X to OY to OX. Okay, and now given a sheaf of Y modules, you can take
Что такое вот это йота или вот это?
yeah,
Вот это
the
идеал.
sheaf of ideals, the sheaf of ideals of X inside Y.
Maybe we need a push forward of OX because it doesn't make sense otherwise.
Okay. Let me write it this way. Yes, okay. Okay, so I sometimes this I lower star is omitted because somehow it's presumed. So we can, given now a sheaf, say N, a coherent sheaf on Y, we can restrict it to X in the sense that we take N modular JX times N, and this is nothing but the tensor product. So this is OX tensor over OY with N. Okay, and this is now denoted I upper star of N, and this is not I inverse of N. So in the home assignment, you had this notion of general pullback, and it is, and in this upper star you use the ringed structure, right? The general pullback works for arbitrary spaces, not necessarily ringed spaces. But now we have explicitly used the ringed structure, so it's something different. Okay, so this is the restriction to x in our coherent setting. There's the restriction to x, and in fact, it can be defined more generally for arbitrary morphism of algebraic varieties, not necessarily closed embedding. And we will discuss this next time. But for closed embeddings, this is very explicit. It works like this. Okay.
Почему вот эта последовательность точна?
Pardon me?
Почему вот эта последовательность с пучком идеалов точна?
Just by definition, maybe. I don't know. Just.
По-моему, такое упражнение было.
Yeah, I think it was in the Homo assignment.
Oh, great. Thanks, Altan. Saved me. Okay. So now it was some general discussion number 2. Now the next example, number 3. Let's apply this general discussion to some particular case, namely, say, X a smooth variety. And we didn't have such a notion before. We'll only have it maybe after New Year. I apologize for such slow pace. But at least intuitively, everybody understands what it means. So let's proceed at this level of, oops, sorry, something happened. What should I do? Sorry. So a smooth variety. Then there is an embedding, the diagonal embedding. And it's closed. So we can consider restrictions as before. Moreover, let me consider the following thing. Let me consider the sheaf of ideals of the diagonal. O XX, O delta X, so to say. Okay, and then I can consider this ideal squared. Okay. Squared. And then I have something in the quotient, and this quotient clearly is supported on the diagonal itself. So on X, and it's called omega 1 X. Or if Ivan again says that it should be viewed as a how to say. So by construction, this sheaf omega 1 X is a sheaf on the X squared, right? But then clearly the ideal of diagonal X by 0 on it, so it's supported actually on X, and it comes from X. Okay, so I don't know how to depict it, but so it's supported on X. It really comes from X. So it's actually a sheaf on X, not on X squared. Okay, and then again, maybe after New Year, we will see that this omega 1 X is the sheaf of differential one forms on X, in case X is smooth. And now something nice happens, you can somehow literally repeat this definition for arbitrary, maybe separated variety X. Yeah, yes.
Сейчас.
Маша, yes.
Да, тут написано какие-то... Я посмотрю на строчку, где омега-1х равняется дельта с звездочкой омега и поделиться.
But I I don't know what would you want me to write. Okay, well, let me write something else.
Maybe it's better to write omega 1 of delta x. So it's diagonal.
Okay, let me write this. Masha, is it okay now with the help of Altan? So it's some sheaf on the square, but this sheaf on the square actually comes as the push forward of some sheaf on the diagonal itself. Okay, so I just view it as a sheaf on the diagonal. So this is the sheaf of differential one forms in case X is smooth. And in general, if you just repeat literally this definition for arbitrary separable X, you obtain something. And this something is the so-called sheaf of Keller differentials. Well, somehow it plays the role of differential one forms in general for singular X. That's some advantage of algebraic geometry. Yeah, you cannot do something in differential geometry as easily, but in algebraic geometry it comes for free. Okay, now the next example 4 is about line bundles, but maybe on projective space. So we say that M is an invertible sheaf if it is locally free of rank 1, and it is invertible in the following tensor sense. So if we have two locally free sheaves, if say F and G are locally free, then their tensor product over OX is also locally free. So the locally free sheaves form a monoidal subcategory inside coherent sheaves. In fact, you can tensor any coherent sheaves that form monoidal category themselves. But what is good is that if now M is invertible, then you can take the local home over OX from M to OX, and this is denoted by M dual. This is also locally free of rank 1. That is invertible. And moreover, the tensor product of M and M dual over OX is nothing but OX itself. So this is the meaning of invertibility. With respect to this monoidal structure, if certainly OX is the unit object, and these are invertible, right? So that the M dual is the inverse. Okay. Okay, so now in case X equals the projective space, the projectization of some vector space V of dimension n+1, say given some positive integer, we can define the following locally free sheaves, invertible sheaves. O of k on Pn. In fact, you had this in your in the last home assignment, but let me give some maybe better definition, because there are used some relation between locally free sheaves and vector bundles, and then you had some tautological line bundle, and then you dualized it. But here is a direct definition. So the sections O of k over some open subset U is the following. So we have this projection from pi from V without the origin onto Pn, and now you have the preimage of pi. So at the global sections of this preimage with coefficients just in the structure sheaf OU. And then, as we discussed quite a few times, there is an action of dilations on this. Okay, and I take the functions homogeneous with respect to dilations of degree k. So functions homogeneous.
Определение сейчас напишем.
Right. So this is by definition. The global, the local sections of OK over some open subset U is the functions on its preimage in the vector space that are homogeneous of degree k. Okay, and then from this, so first of all, maybe it's an exercise, but rather evident that this is really that this is a really line, really an invertible sheaf. So it's locally isomorphic to the sheaf of functions, that is degree 1 function, degree 0 function, and then it's also clear that if you tensor O of k with O of L over O, the structure sheaf, then you obtain O of k plus L.
Misha, and
yes.
And what is this OU that you take the global sections? Maybe it should be O of V without the origin or something.
It doesn't matter. It doesn't matter because the origin is just one point, and it doesn't affect the functions, the global functions.
Okay,
right?
so it's O and the index is V, yes, not U.
No. Sorry. Yeah. O. Yeah. Thank you. All right. Thank you. Yeah. Now.
Как вот это определение связать с тем определением, которое у нас было в домашней работе?
Well, maybe that's another exercise, but I think this is an easy exercise, rather straightforward. Okay, and finally, O of negative k is O of k dual. Okay. So these are the basic examples that we will encounter over and over again. And now let me consider one very important particular case. So in this case, the closed embedding of a subvariety
Можно
into
вопрос?
something. Yes.
А вот
Pardon me?
почему, да, вот почему, ну, собственно, произведение тензорное в этих двух последних очков будет, собственно, ну, тогда как доказать, что он обратим? Условно.
Well, just it's a general fact that if say M and L are invertible, then M tensor L or X is invertible as well. And this is absolutely clear because they are locally free of rank 1. When you tensor them, you again obtain a locally free sheaf of rank 1. Yeah, there's no question about this. And the dual is just M dual tensor L dual. So there's no question about this. And then you only have to identify it with OK plus L. And then it's again a local question. Just because when you multiply functions of degree K and L, you obtain a function of degree K plus L. So there is no problem with this. Okay. About this restriction, let's consider a closed embedding like this, just a point into some ambient variety. Okay. And then given a sheaf M, you can take its restriction to this point. Maybe let me call it I sub X and take its restriction. Then this is the fiber of M at X. Okay, this is the fiber, and we already discussed this, but let me stress that this is not the stock of M at X. Okay, not the stock. Maybe let's consider the following example.
Не то же самое, что и минус 1 раньше у нас было.
Oh, no. This is the restriction with the use of ringed structure. Yeah, that's the pullback, the ringed pullback.
Спасибо.
Okay. Yeah, in fact, yeah, that's a very good comment. Okay, this is just I inverse of M. Yeah, so you can take the stock. It's just the general pullback I inverse, and it can take the fiber. This is the ringed pullback I upper star, and these are different things. And let's consider the following example. So say X is an irreducible algebraic variety, and then there is the field of rational functions. K of X. Okay, and we can consider the constant sheaf with such a stock on X, and somehow probably this is essentially the only example of a sheaf which is simultaneously constructible and quasi-coherent. So this is a quasi-coherent sheaf. Okay, namely, it is the localization, so to say, of this module. Okay, so it's a very useful quasi-coherent sheaf, but somehow very simple-minded, just a constant sheaf. All the stocks are the same. They are all equal to the field of rational functions on X. Okay, and now let's do in the real time the following exercise. What are the fibers of this sheaf? Well, Igor Saban, how do you think? What is the fiber of the sheaf at the point X small?
Так, надо посмотреть на росток.
All the stocks are just the same field of fractions. Yeah, that we know. The question is, what are the fibers? The stocks are big. What are the fibers? They are small.
Теперь надо факторизовать по
Absolutely.
максимальному идеалу.
Yes, the definition is this, but what is the answer?
Наверное, просто поле К.
Pardon me? No. No. And say, Anfisa, do you know what's the answer? By any chance? I can't hear you. I couldn't hear you. But Igor, do you know? Vanya, Ukrainцев, do you know?
Can you repeat what do you mean by fiber?
Oh yes, this is by definition. This is our module. This is the ring of functions. Now you tensor over the structure sheaf with the ring of functions on this small x. Now this ring of functions is just k, small k. Okay. Or if you want, I can rewrite it once again. The same big field. You tensor over the local ring of this point with the base field small k. So what do you get?
Oh, rational functions?
No.
Is that a small k?
Yes. In fact, this is what Igor Chaban suggests from the very beginning. Yeah, I'm sorry. Yeah. Sorry. Yes, you do just this. You get just this. So you see that the fibers are small and the stocks are big. Okay.
Можно, пожалуйста, повторить определение и со звездочкой, потому что или оно у нас где-то раньше было.
Oh yes, just we have this.
Может, на предыдущей странице.
Yeah, certainly. So we have this exact sequence, the maximal ideal of this point, and if you want, you can localize it, or just let's localize.
Ну, не для вложения, а для произвольного отображения.
No, we did not define for arbitrary morphisms, just for closed embeddings. Okay, K, it's a skyscraper sheaf.
Вижу, да, спасибо большое.
Okay, and now we just tensor with this. Okay, so I x star of anything is just kx tensor over O with anything. Okay, this is the definition. Okay.
Okay.
Okay. So now let's but I'm still confused. Maybe maybe I was wrong. Still, I think that maybe you'd rather get 0 here. How do you think? Maybe it's rather 0.
We are all confused too, just as you.
So I would vote for 0.
Ну кажется, что вот у нас
Yes.
есть поле от x,
Yes.
и в нем есть какой-то как бы максимальный идеал, да, который пришел из локализации вот OX. Но он должен быть максимальным, но не нулевым. Значит, он как бы должен совпадать со всем k от x.
Yeah. So, or in other words, say the maximal ideal is generated by some functions vanishing at small x. Yeah, and then you declare them to be equal to 0, right? On the other hand, in this big field of rational functions, they are invertible. Okay, so it means that the total tensor product is 0, right? Because on the one hand, they are invertible in the left factor. On the other hand, they vanish in the right factor. So they are 0. Okay, so sorry about it.
It wasn't still it wasn't too clear.
Why?
But okay, can you repeat, please?
So let's consider the operator of multiplication by.
Maybe the upper line is confusing, where you tensor k of x with ox.
Over OX, yes. But it's the same as to take the tensor over the local ring.
Well, no,
Yes.
if you tensor over OX, then the field will be, then the fiber will be k of x.
No.
You should take the local ring, exactly as you said.
But that doesn't matter. Once again, let's take any function, say global function that vanishes at small x.
Well, constant function is also a global function, but it's also a rational function. So we can pass from k to k of x.
Yeah. But still, I want to take a function that is not constant, but is vanishing at x. At small x, at the point
That
x.
doesn't, but it isn't indicated in the upper line.
What do you mean by indicated in the upper line?
Comma x. You should write comma x.
Here.
But
it doesn't matter. When I multiply with so that this small field k is a module over the structure sheaf. It's a skyscraper at the point small x. It's a model over the structure sheaf OX that somehow factors through the stock at this point, through the local ring OXX. Okay.
So the k in the upper line is not a constant sheaf, but it's a skyscraper sheaf at the point x. Is it?
This is the constant sheaf, and this is the skyscraper sheaf at the point x. Yes.
Now it is better.
Okay. And here again, and that's just 0. Sorry about this confusion.
Сейчас. Я чего-то в жизни не понимаю. Вот мы вообще, когда берем и со звездочкой, мы получаем пучок где?
It is,
вот если мы откатимся на несколько страниц назад, у нас там где-то было определение.
Yes, so we had this general situation, x embedding into y, then I upper star m was a sheaf on x. Okay, of OX modules. Now, in this case, our left-hand side is just one point. It will be a sheaf on just one point. So, in other words, just a vector space. And this vector space turns out to be 0.
Okay, and how do we define it again? So,
how do I define what again?
I upper star. So maybe you can just show the page.
The ideal of x in y, y, ox 0, and I upper star m is the tensor product ox tensor over oy with m, or in other words, this is m modulo this ideal. Is it okay?
Perhaps maybe you can write it for an arbitrary, just an arbitrary open subset of x, because I'm so confused. So if
for general f, you do this locally over open subsets, yes. But in the upper half of the page, we apply it to the case of just one point. So there are no open subsets, just this point itself.
Wait, but what you write in here is a sheaf on y. Because M calligraphical is a sheaf on y.
So that's why I am confused. Maybe you can write just like the general definition for like I upper star m on an open set.
The push forward of certain sheaf. I don't know. Uniquely defined. Sheaf on X denoted I upper star M as well. Okay. So given a sheaf on Y, you produce another sheaf on Y. It is supported on X. Moreover, it comes as a push forward of certain sheaf on X, and this sheaf on X is just this pullback.
So maybe you should try just before all this line of equalities, you can write I lower star, and it will be a correct definition, perhaps.
Okay.
Yeah, like that.
Very good. Yes.
Thank you.
Yes. Thank you very much. So now I hope the misunderstanding is cleared. Absolutely. Totally.
Можете еще раз повторить, почему 0 получился?
Just because we tensor two things. One is invertible, another is 0. And that's it. It's like when you tensor z over 2z over z with z over 3z, and you get 0. Just because multiplication by 2 is invertible in the right-hand side, but it's 0 in the left-hand side. And multiplication by 3 is invertible in the left-hand side, but 0 in the right-hand side. So both 2 and 3 are 0. And this means that 1 is 0 and everything vanishes absolutely. And the same argument works here. Yeah, you can produce the functions that are invertible in this field of fractions, but are 0 in the right-hand side. Okay? And they all act by 0. On the other hand, they generate the whole ring. Okay, so everything is by 0.
Спасибо.
Welcome.
And
Yes.
I'm sorry, but I have now the question.
Yes.
Is it obvious that the sheaf is uniquely defined by this condition? Like, what do you have to check?
You have to check that the action of the structure sheaf of Y factors through the action of OX. Okay, and this is by the very definition, because you exactly killed the ideal of X. So now the action factors through the action of OX. So the sheaf on OX, okay, of OX models.
Yeah, I see.
Okay.
Сейчас, еще, возможно, кстати, надо написать под вот в этом же самом определении и со нижней звездочкой OY, чтобы это было тоже, ну, тензор хотя бы над одним пространством. Нет?
You mean here? No, I think or maybe no. OX is a sheaf of Y modules. No, I think that here everything is perfectly correct. Yeah, both OX and M are sheaves of Y modules, right?
Okay.
Yeah. So I think here it's fine.
Okay.
Misha, maybe the last question about this tensor multiplication in Y to 0.
Yeah.
I have a question that you have constant functions both in both terms. So I think that the image should be also constant or not.
But let's act on this constant function by a generator of the maximal ideal. Yes. So this generator of the maximal ideal is invertible in the big field of rational functions. So this action must be invertible. Do you agree?
Yeah, so I see. Okay,
on the other hand, it's 0 from the point of view of this skyscraper small field, right?
Yeah, thank you.
It's simultaneously invertible and 0, so the whole thing is 0.
Я ужасно извиняюсь, но вот я просто правда ничего не понимаю. Вот у X это пучок где? На X, правильно? И мы умножаем на пучок на Y. Что-то как бы не так. Наверное, здесь тоже еще и со звездочкой где-то не хватает.
But you see, OX is a sheaf of Y modules. Don't you agree? So X is a closed subset of Y. So any sheaf on X is simultaneously a sheaf on Y. Well,
it seems like actually, Masha expresses the same complaint I was expressing before. We have to write I star O of X. Otherwise, it will be confusing.
That's what you want.
Yeah.
If it makes you happy, then I'm happy too.
It does.
So is everybody happy now?
Yes.
Great. So where were we? We were considering fibers, and to make you, all of you, unhappy once again, the fiber of M at X will be denoted M sub X. So it's hard to distinguish it from the stock, but maybe it will be possible in our context. Okay. So you're welcome to ask me what I mean every time when I write M sub x. But from now on, it will be mostly fibers. Okay. So hope there will be no confusion with stocks. For coherent sheaves, we will usually consider just fibers. And that's the reason why, just by Nakayama lemma, if, well, so maybe not if, but let's assume, take a coherent sheaf M on X, and the point in X, then the fiber at this point is 0, if and only if M is 0 in a neighborhood U of X in X. Okay. So this just literally Nakayama lemma we had in our set of exercises. Maybe not number 2 or something like this. Okay, just because we know the localization, we know that the M is a localization of some module M, and the fiber at X is the following thing. You first localize M at the maximal ideal of X. It's localization with respect to the multiplicative subset S equals A without maximal ideal, and A is the ring of global functions. If X is affine, but our question is clearly local. So once again, I take this localization and then I just kill the maximal ideal. Okay, and then if I know that this quotient is 0, then by Nakayama lemma, I know that the model itself is 0. But to this end, it was necessary to know that the model was finally generated, right? And we just discussed for 40 minutes the example when we had the infinitely generated module, namely the field of fractions, where this was not true. Okay, so we use that M is finally generated. Okay, and now let me prove the following proposition. That again, we have a coherent sheaf M coherent sheaf on X, and then the following statements hold. So let us have a few sections, sigma 1 and so on, sigma n. Are certain sections, and actually the question is local, as you will see in a moment. So there is a big supply of sections. And now consider the homomorphism from OX.
Professor, I'm sorry, may I ask a question?
Yes, yes.
Yes, for the Nakayama's lemma, and I see that you have shown that if the fiber is 0, then the stock is 0, right?
Right.
And then how do we find the open subset that M vanishes?
But the stock is 0 just by definition. The stock is the direct limit over the neighborhoods, right? So if the stock is 0, it means that for some neighborhood the sections must be 0. You see?
Thank you.
Just by the very definition. Okay, so there is a map like this, namely the standard basis E sub I goes to sigma sub I. Okay, and this map, well, let's call it, say, phi. So phi is onto well, in the fiber mx, if it is onto in some neighborhood okay, and in fact this is just well, again, it's just Nakayama lemma, maybe a version of Nakayama lemma. Now the second claim is that if we consider a function but it's not a usual function. It's integer valued function. So how should I denote it? Delta from x to positive integers, namely delta of x is the dimension over our base field of the fiber at this point. Okay, this function is upper semi-continuous. It means that the pre-image of some interval from 1 or maybe 0, from 0 to R is open in X. Okay, and somehow intuitively in words, the dimension of fiber can only jump. Yeah, it can, under specialization, it can only jump. If your point somehow goes to some limit, then in this limit, the dimension of the fiber can only jump, cannot drop. And finally, delta is a constant if and only if this M is locally free. Okay, so we have a very explicit criterion when a coherent sheaf is locally free, just when all the fibers have the same dimension. Okay, so let's prove it. So one is just Nakayama lemma, nothing new. Now, for two, let's say that the dimension of the fiber is n, and then we want to prove that the set of points where the dimension is less than or equal to n is open, so it contains a neighborhood of x. Of small x. Okay, so to this end, we choose a basis of this fiber and lift it to some sections sigma 1 and so on, sigma n of M in a neighborhood U of small x. Okay, and then, oops, sorry. So then we see that those sigma 1 and so on, sigma generate M in a smaller neighborhood. Say U prime inside U of X just by number 1. And there we are. So since they generate, the dimension of the fiber must be less than or equal to n. For y in this U prime, dimension of fiber is less than or equal to n. Okay, so there we are. And number 3, the criterion of being locally free is so if it is locally free, then certainly all the dimensions of fibers are the same. This is clear. And conversely, so again, suppose that the delta function, the dimension is everywhere n, and again choose sections local sections. Sigma 1 and so on, sigma n generating M in a neighborhood of our point X. So choose some point x, choose local sections generating the fiber at this point. Then they generate the sheaf M calligraphic in some neighborhood of this point, and so we get morphism phi that is surjective from OU to the power n to M restricted to this neighborhood U. Okay, and now let's consider the kernel of this morphism phi. Okay, then we know that the fiber, so it's a coherent sheaf. It's a subsheaf of OU to the power n, so it's coherent. Well, let's denote it by K calligraphic. Then K is a coherent sheaf. And its fiber at point x is 0. So K is 0 in a neighborhood U prime of x, right? And hence phi is an isomorphism in this neighborhood U prime. Okay, so it means that M U prime is free and M is locally free. Okay, so we proved this theorem, and it's very important and used all over and over. But unfortunately, somehow I lost all the time in discussions, and we have to stop now. So I apologize for the confusion I caused. Okay, so now I'm saving the notes. Maybe somebody has questions.
Actually, I have a question.
Yes.
Suppose we have a context of the problem when you have a sheaf of algebras, like in the problems.
Yes.
And you define the spectrum of the sheaf.
Mm-hmm.
Is it true that the dimension of a fiber of a sheaf is the same thing as the dimension of the preimage of a point?
No. In the case you describe, the sheaf of algebras will be only quasi-coherent. Yeah, I mean, by very definition, if the sheaf of algebras turns out to be coherent, then the corresponding morphism of spectra is a finite morphism. Yeah. So if you don't consider the finite morphisms of algebraic varieties, then the direct image of a fine but not finite morphism is necessarily not a coherent sheaf, but quasi-coherent. It's very big, so the dimensions of fibers are infinite.
Mm-hmm.
But the coherent sheaves are very small, and that's why the Nakayama lemma works, and the arguments like we just had work. But the sheaves we considered in this problem 2 or 3 in the home assignment, they were only quasi-coherent. They're very infinite dimensional in general. Does it answer your question? Okay. And any other questions?
У меня есть еще один вопрос. Он не совсем про это, а скорее про... Вот если у нас есть афинное многообразие, у меня такой вопрос. Вот существует ли такое... Ну, у нас есть какой-то афинный морфизм, вот, между двумя афинными многообразиями. Существует ли такое покрытие, афинное многообразие, там тоже афинным многообразием, так что пересечения были тоже афинные? Всегда ли такое существует?
Oh, yes, we just proved it. A few times ago, we just proved it. It was a sort of criterion of separability. If your variety is separable, then what you say necessarily holds true.
И для афинных, получается, работает.
Oh, yeah.
Хорошо.
Any other questions?
Можно спросить, вот когда мы определяли pullback со звездочкой, я не совсем понял, как мы использовали точность последовательности, как точность последовательности связана с определением.
Well, I just compute the tensor product explicitly. So instead of writing tensor product, I wrote just the quotient model of this ideal. Because of this exact sequence.
Понятно. А вот когда мы вкладывали два многообразия, говорили, что они замкнутые вложения. Нам потребовалось, как мы использовали, что оно замкнутое?
The structure sheaf of the smaller variety is the quotient over the structure sheaf of the bigger variety. Otherwise, it's not true. Only for closed embedding.
Ну, а где мы вот тогда использовали, что это тогда фактор пространства, фактор пучок? Или вы что-то имели на другое?
So the structure sheaf of X is the quotient of the structure sheaf of Y if and only if X is a closed subvariety of Y.
И дальше мы говорили, что это позволяет нам говорить о серьезном...
I can't hear you anymore.
Хорошо, спасибо.
Welcome. Okay, so then I'm saving the notes.
А можно еще спросить?
Yes.
Для ростков есть конструкция, когда мы склеиваем ростки, получаем пространство такое, что наш пучок оказывается пучком сечений. А для слоев можно такое сделать?
Well, in a sense, yes. Just in the last home assignment, this was the way to obtain a locally free sheaf as the sheaf of sections or vector bundle, right? But the fibers of this locally free sheaf will be exactly the fibers of this vector bundle.
Это для локально свободного, а получается когерентно так не будет работать.
I would say no.
Спасибо.
Welcome. Okay, so if no more questions, then I stop the recording.